In this video, we'll look at a heat transfer analysis for cylindrical well pipes, focusing on the concept of the overall heat transfer coefficient. We begin with Fourier's law of heat conduction, which describes how heat flows through a material. In cylindrical coordinates, Fourier's law tells us that the rate of heat transfer Q depends on the thermal conductivity of the material, the area through which heat flows, and the temperature difference across that area over a small radial distance. For a cylindrical pipe, the area of heat flow is the surface area of the cylinder given by 2 pi r times L, where L is the pipe length. By rearranging the equation, we can integrate Fourier's law to find the temperature distribution within the pipe wall and the overall heat transfer rate. An essential concept here is thermal resistance, analogous to electrical resistance but for heat flow. We can express the heat transfer rate in terms of the temperature difference and the thermal resistance. Next, we introduce the effective heat transfer area. This concept simplifies calculations by representing the geometry of a cylinder as a single equivalent area. Through integration, we get the ratio of the temperature difference to the radial distance. By equating this with the heat conduction equation we previously derived, we find the expression for the effective heat transfer area. Here, Rho is the outer radius and Ri is the inner radius. We also consider the transfer of heat through fluids in the annulus of the well pipe. Using effective area expression we derived, we expand the heat convection equation, noting the presence of the mean radius. Rearranging the equation, we extract the corresponding thermal resistance, denoted as Rv. Now let's bring it all together with one example. In this well, we have 4 layers of different material components, and we measure the temperature of the inner and outer surfaces ranging from T1 to T5. In the third layer, between T3 and T4, heat is transferred radially via convection. In the remaining component layers, heat is transferred radially via conduction. We write out the heat transfer coefficient for all components as a function of their respective temperature differences and thermal resistance. By rearranging the equations and recognizing that under steady-state conditions, the heat transfer in each component is the same, we can substitute the individual heat transfer rates with a single Q. When we sum up all the terms, the equation simplifies to the heat transfer rate multiplied by the sum of thermal resistance equaling the difference between T1 and T5. We generalize the equation to this form, where n is the number of well components and Tn plus 1 refers to the temperature at the outer surface of component n. The summation of thermal resistance is inversely proportional to the overall heat transfer coefficient U. A is a reference area, normal to the direction of the heat flow, which we will introduce soon. The summation of thermal resistance can be decomposed into a series of thermal resistances, the conduction term and the convection term. Each term is substituted by the thermal resistance of the respective heat transfer mode. Here, we replace the heat conduction term, and similarly, we replace the heat convection term with the corresponding expression. We are now ready to relate the series of thermal resistances to the overall heat transfer coefficient and the reference area. If we define the area based on the inner radius of the well pipe, R int, the area term becomes 2 pi r multiplied by R int. Rearranging and simplifying, we get the expression for U, the overall heat transfer coefficient. This single value considers all the thermal resistances mentioned in this video, indicating how easily heat flows through the entire well structure.